Last segment we discussed about how to represent a particular vector in many ways, especially when we need to calculate something with the vectors and when we need to derive something. Okay. If you remember, the symbolic way, the pictorial way are for the generic derivations, and for calculations the component form and the unit vector form. So, these are the four important representations of the vector, and before that we had studied about the distinction between equality and equivalence, and now we will define three more terms with respect to equivalence of vectors, which are also very important to characterize a particular vector in a particular situation. So, they are free vectors, then we will say transmissible vector, and bound vector. It's always helpful if we can always characterize a particular vector by any of these things, so that it will be easier once we go to the conditions or situations where we need to find out the resultant or the simplest form of a very complex system of forces. These concepts will be useful. So, now, and then all these things are with respect to equivalence of forces. Okay. Now, let us see what they mean. A free vector is also, as the name suggests, means suppose you have a axis, define the space. Okay. Now, you are free to draw the vector anywhere. Like suppose I will draw the vector here, or I will draw the vector maybe here, so it is parallel. Okay, yeah, more or less. I draw the vector here. So, basically what I am doing is doesn't look like the length is, yeah, wherever I draw, I am not changing the orientation. Okay. That means the angle that this vector is making with, say, the y axis, the z axis and the x axis, these angles are not changing, neither the sense is changing. So, it is always pointing upward in a way. Okay. So, these are remaining same. What I am doing is just changing the line of action of the force, okay, through which the force is acting, force or the vector. Okay. It did not necessarily be a force, it could be just a vector, any vector. Okay. Now, if we just are changing the line of action without changing the orientation or the magnitude, okay, then and then on doing so, if the effect under consideration is not getting affected. So, this is the definition of a free vector. The vector A will be called a free vector if by changing the line of action to whatever point we wish, the effect under consideration is not getting affected, it is not changed. then the vector is called a free vector. For example, suppose this is this vector suppose represents the velocity of this particle. Okay. Now, if I draw this vector or this vector to represent the velocity, and if the effect which I am concerned with is the displacement or the distance or the displacement that the particle is making, then will it matter where I am representing this vector, the velocity vector? It does not, because the displacement will always be the same irrespective of what is the line of action of that vector. Then under that condition, that means under the effect that I am concerned with the displacement of the particle, the velocity vector is a free vector. We will, so this is not a very illuminating example of free vector. We will come back to a beautiful example once we come to couple moment in a couple of segments. Now, okay, so there you will realize how important it is to in fact recognize that a vector is free. Okay. Then you will do a lot of things by moving it around to cancel with many other things. Okay, we will see that, but for now just concentrate on the definition of the free vector. Okay. Now, having said that, what is a transmissible vector? Now, here what we are doing is the line of action remains same in the case of transmissible vector, and you are free to move it anywhere. For example, suppose there is a body lying on the ground. Okay, so this is the ground, and I have a body. Okay, and I am applying a force. Okay. Now, if I am applying this force on this body, and for a moment imagine that it's a rigid body, and the effect I am considering is the acceleration that this force is causing on the body. Then will it matter if I apply this force anywhere along this line of action? It does not matter. That means, suppose instead of applying the force by, just imagine that you have attached a thread or something and pulling it. Okay. Now, the thread you can attach here, does not matter, or in the same way you can now push it also by using a stick maybe. Okay. You have now attached a stick to the body, and now you are pushing it with the same force. The line of action has not changed, and you are just pushing it. Then it does not matter, right? The acceleration will be exactly the same, this force over this mass. Now, under such condition, the force will be considered as transmissible. Okay. So, many situations will come, very soon we will be seeing that by considering this transmissibility, a force can be moved from one point to the other, so that it will be easier for calculation purposes. Okay. To simplify the system of forces, suppose there are 10 forces, to make it to say 3 or 4 forces or even one force. So, these kind of concepts of transmission of the force along the line of action will be useful. Now, suppose we were imagining till now that this body is rigid, and now you imagine that the body is say a flexible body, it is like a jelly. Okay. If you pull it, it gets extended, maybe it becomes something like this. I'll do that, something like that it becomes. Okay. Now, but still even if you push it, it will take up a different shape. Maybe it will take a shape of, say, this type. Okay. If I am pushing it from this left side. Okay. Now, but still the acceleration that this force is causing is exactly the same. Okay. It does not matter. So, as long as this line of action is remaining the same, so it does not matter. But now, if my effect or the phenomena, the phenomenon which I am concerned with, if that is changed, and now I am concerned with the deflection, type of deformation which is caused by the force on the body, then definitely this force is not transmissible. Okay. Now, because the pulling, the effect is different, actually the body gets elongated, sorry. By pushing, the body gets slightly compressed. Okay. So, if the effect I am concerned with is of deformation, then the force shown here is not transmissible. So, that point needs to be completely kept in mind. Okay. So, then free vector and transmissible vectors are done. Then what is bound vectors? So, as the name suggests, they are completely bound to a point. Wherever you have applied, so they are completely, you can't do anything. Okay. Suppose in this case, when we consider the body to be flexible, okay, so then the force actually became bound. Now, if you put the force here, the effect is one. If I put the force here, the effect is completely different. And similarly, at any other point, if I somehow attach the force here, the deformation will be completely different than the other two types of deformation. So, every point, if I attach the force and try to pull or push or apply that force, the effect is going to be different. So, that makes the force under the effect of consideration of deformation, the force is a bound vector. So, these three types of vectors you should always keep in mind and use them very judiciously to simplify the system. We will see in a couple of segments later. Okay.